Hello and welcome to a lesson on logarithms. So last class we started talking about what logarithmic functions are. Recall that logarithmic functions are inverses of exponential functions. So in this lesson we're going to talk about logarithms in more detail, and we're also going to simplify expressions that involve logarithms. So when solving exponential equations, we have the tools to do this only when we can create two like bases. So for example, here we have 8 to the exponent of x is equal to 1 over root 2. So take a moment to think about how you would solve this equation for x. So I would recommend pausing the video and trying to solve this equation. All right, so let's have a look at how this equation is solved. So the common base in this case is 2. So I would change the 8 to 3 to the exponent, so 2 to the exponent of 3 to the exponent of x is equal to 1 over, and so I'm going to write the 2 here as 2 to the exponent of 1/2. Recall that's what a square root is, right? A square root is the same thing as raising a base to the exponent of 1/2. Okay, so now this turns into 2 to the exponent of 3x is equal to 2 to the exponent of negative 1 over 2. So what I did is I brought the 2 from the denominator up into the numerator, and the sign of the exponent changes. Now what we can do is we can drop the bases. We can drop the 2's. And we end up with 3x is equal to negative 1 over 2. And now we would divide both sides by 3, and we would end up with negative 1 over 6 as our final answer. Now you might remember doing this solving exponential equations in grade 11. So then this might be familiar to you already. Now, how then can we solve something like 1 over 2 to the exponent of x plus 1 is equal to 3, where it's not possible to get a common base, right? So 1/2 and 3 do not have a common base. And so we're going to actually come back to this towards the end of the lesson. So logarithms actually allow us to solve exponential equations where it's not possible to get a common base on both sides. So recall that the inverse function is obtained by interchanging x and y values. And graphically, what we're doing is we're reflecting over the line y is equal to x, the diagonal. So we did this in the previous lesson already, but let's review this. So let's start by graphing y is equal to 10 to the exponent of x. And then we're going to also try to graph the inverse as well. So take a moment, pause the video, graph the function y is equal to 10 to the exponent of x, and then also try to graph the inverse. And if possible, also try to write down what the equation is of the inverse. All right, so starting with y to the exponent of, or y is equal to 10 to the exponent of x. So at 0, so when x is 0, y is 1. Recall that all exponential functions generally pass for 0 and 1. When x is 1, y is 10. When x is negative 1, so 10 to the negative 1 is 1 over 10, so which is a very small value. And so if we graph this, this is what it's going to look like. Okay, so y is equal to 10 to the exponent of x. Now let's also sketch the diagonal. So y is equal to x. And so now for the inverse, we're going to reflect along the diagonal. So now we're going to have a point at 1 and 0, and we're also going to have a point at 10 and 1. And then another point here at about 1 over 10 and negative 1. So if we graph this, we're gonna have a function that looks something like this. Okay, and so this function can be written in two ways. As we've seen before, it can be written as x is equal to 10 to the exponent of y, or a new way of writing it. Okay, so f inverse of x is log to the base 2, well, not base 2, actually base 10 of x. Okay, so this is a logarithmic function that has a base of 10. And that's the notation that we use. Okay, so yeah, so as mentioned already, so this function is a logarithmic function, the inverse of the exponential. So f of x is defined by y is equal to 10 to the exponent of x. If we interchange x and y, we get f inverse. And the inverse function is defined by x is equal to 10 to the y. Now, the relationship is then as follows. So y is equal to 10 to the exponent of x can also be written as x is equal to log to the base 10 of y, or log y. Okay, so that's another way to actually write this. Now we're going to look at how to convert from exponential form, which is this form here, to logarithmic form, which is this form here. Like how do we go from something like this, an exponential equation, to a logarithmic equation? So what we basically have here is we have the answer. So the answer is y in this case is equal to the base, which is 10, to the exponent, which is x in this case. And what we end up getting is we get our exponent, which is x, is equal to log, which we have here, to the base, so same base that we have here, so this 10 base. So log to the base of the answer. The answer is y, okay, because 10 to the x is equal to y. Now the most common base for logarithms is 10. And if it is not written, then you assume that the base is 10. So sometimes you're going to encounter where the base is not going to be written. So this 10 is not going to be written. So what you'll see is just y is equal to log x. In those instances, assume that the base is 10 if no base is written. Another way of thinking about it is y is the exponent to which 10, the base, is raised in order to get x. Okay, so that's another way of thinking about it. So we write this as, already I wrote this earlier, but this function is y is equal to log to the base 10 of x, the function that we just graphed earlier. All right, so now let's have a look at how we would convert from logarithmic form to exponential form and vice versa. So we want to write an equivalent exponential statement for log to the base 10 of 1,000 is equal to 3. Okay, so take a moment to think about how you would do that. You want to apply this here. Okay, that if we have log to the base of something of an answer, right, that's equal to the exponent, right? And we want to convert this into this. The answer is equal to the base to the power of the exponent, or to the exponent. All right. So we have basically what we think. The way we think about this is 10 to the exponent of what gives us 1,000. Okay, so 10 to the exponent of 3 gives us 1,000. So the way we can write this in exponential form would be 10, the base, to the exponent of 3 is equal to 1,000. Okay, so that's going from logarithmic form to exponential form. Now, let's try going from exponential form, this is exponential form, to logarithmic form. So we want to write an equivalent logarithmic statement for 3 to the exponent of 4 is equal to 81. Okay, so take a moment to try this out and see if you could write the logarithmic statement. All right, so how this is going to look like, it's going to be log to the base 3 of 81 is equal to the exponent 4. Okay, so log to the base 3 of 81 is equal to 4. So another way to think about this is 3 to the exponent of what gives you 81? And that would be 4. All right, let's look at another example. So without using a calculator, find log to the base 10 of 100, or just log of 100. So how do we do this? We can set this equal to x first, and we can change this to exponential form. So in exponential form, it's going to look like this. It's going to be 10 to the exponent of x is equal to 100. We can get a common base. So 10 to the exponent of x is equal to 10 squared. Right, 100 is 10 squared. We can drop the bases, and we get x is equal to 2. Okay, so 10 to the exponent of 2 gives us 100. All right, let's look at another one. So once again, I'm going to set this expression equal to x, and now I'm going to convert from logarithmic form to exponential form. So 2 to the exponent of x is equal to 32. Now we want to get a common base. In this case, it's 2. So 32 can be written as 2 to the exponent of, well, not 6, to the exponent of 5. So 2 to the exponent of x is equal to 2 to the exponent of 5. Now that we have a common base on both sides, we can drop the bases and get x is equal to 5. So 2 to the exponent of 5 gives us 32. All right, let's also do part C now. So for part C, again, I'm going to set this equal to x. And I'm going to write this as log to the exponent. So log to the base 5. I'm going to write 0.2 as 1 over 5. Okay, and so now converting to exponential form is going to be 5 to the exponent of x is equal to 1/5. Now 1/5 can be written as 5 to the exponent of -1. And now we can drop the bases and we'll get x is equal to -1. So the way you think about all of these is basically the base to the exponent of what is going to give you whatever is after the base in that statement, right? That's the way to think about it. All right. So moving on to this example here, we want to evaluate these. So we have log to the base a of a to the exponent of n. So if we set this equal to x, and that's always a good idea, and we now convert this to exponential form, then we're going to have a, which is the base, to the exponent of x is equal to a to the exponent of n. Now notice we have the same base on the left side and right side. We can drop the bases and get x is equal to n. And so that's what we get when we evaluate this. We just get n. All right, let's look at another one. So log to the base 2 of 1 over root 2. Let's set this equal to x. And now convert to exponential form. 2 to the exponent of x is equal to 1 over root 2. 2 to the exponent of x is equal to 2 to the exponent of -1 over 2. Drop the bases. X is equal to -1 over 2. All right, now you can also try using your calculator to evaluate these expressions. So log of 1,000. Now this can also be done without a calculator fairly easily. Now recall that if a base is not written, assume that the base is 10. So here we see the base is not written. We have log of 1,000. So the base here is 10. So this can even be done without a calculator. So 10 to the exponent of what number is going to give you 1,000? Right, and that number is 3. Because 10 to the exponent of 3 is 1,000. Now this one, in order to evaluate this one, you're going to have to use a calculator. So since I don't have a calculator, I'm just going to use Desmos as a calculator. Now Desmos is a very good scientific calculator. I guess I actually don't have Desmos installed. Okay, so let me open it up and use it here. Okay, so all you have to do is go through functions, and oh, it seems like there's no log function here, right? Oh, wait, let's see here. There should be. Oh yeah, here we go. Log, yeah. So log. So if it's just log, it's log to the base 10. And I think it was I think it was 52, right? Now let's go back and check. Yeah, log to the base 10 of 52. Okay, so what was it? It was 1.72. Okay, so 1.72 approximately. Okay, so that's just using a calculator. So you wouldn't be able to do this without a calculator because it's not a whole number. Find an approximate value of log to the base 2 of 10 to 2 decimal places. Okay, so what we can do here is we can convert this to exponential form. Now, in the future, we're going to learn how to actually get an exact value for this, but here we're just going to approximate. So we're going to have, if we convert this, we're going to have 2 to the exponent of x is equal to 10. And now what we could do is we could use trial and error. Now, your calculator might actually allow you to change the base of the log to 2. But not all calculators allow you to do that. So if you do have a calculator that allows you to set the base of the log, then you can just use your calculator. Now Desmos also allows you to do that. But what we could do is you could try to just use trial and error. You got to think about, okay, 2 to the exponent of what could give us 10 potentially. So we know 2 to the exponent of 3 is 8, and 2 to the exponent of 4 is 16. Now it's going to be closer to 8 than it's going to be. It's going to be closer to 3 than it's going to be to 4, right? So it's probably around like 3.2, let's say. Okay, so let's try that out and see. So 3.2. So 2 to the exponent of 3.2. Okay, it's actually more than that. So let's go with. Let's erase this. Oops. How do we even erase here? Okay, let's just try this again. So 2.2 to the exponent of, let's go with 3.4. Let's try. Well, that's over. Okay, so it's going to be about 3, right? Yeah, it's very close, like 3 something, 3.2 maybe. No, not 3.2, 3, probably about 3.5. Well, that's over 3.4 then. Okay, yeah, all right. So about, let's go with 3.3. Okay, so yeah, so 3.33 approximately, maybe a little lower. But now, if we actually get the value here, we go to functions, and so log. Here we can set the base, set it to 2, and 10. So 3.3219. Okay, so 3.32 approximately is what we're going to write. Okay, so x approximately 3.32. All right, good. All right, example 7. We're going to write each in exponential form. So we kind of have done examples like this already. So here this would be 4 to the exponent of 3 is equal to 64. Now this has a base of 10. The base is not written. So this can be written as 10 to the exponent of y is equal to 100. Now this one is interesting. Y is equal to ln of x. So ln stands for natural logarithm. And what ln is, it's log to the base e of x. Okay, so e is known as Euler's number, named after the famous mathematician Leonhard Euler. And so it's e is an irrational number. It's approximately 2.71. It's kind of like pi. So basically what we have is we have y is equal to log to the exponent, so to the base e of x. So if we change this to exponential form, the way this is going to look, it's going to be e to the exponent of y is equal to x. So well, how this is going to look like. Okay, and so yeah, here we have e. E is Euler's number, and it's 2.71828, and then it just keeps on going, goes on forever. It's an irrational number. So it's a non-terminating decimal and non-repeating decimal. Okay, so these ones these ones here, excuse me, are we want to convert them to logarithmic form. So let's do that. So log to the base here is 2. So log to the base 2 of 16 is equal to 4. And then this next one here, so log to the base n of m is equal to 3. This one here, log to the base 3 of 1 over 9 is equal to negative 2. Now, these examples here, so we can set this, remember, we can set these equal to x. Right? So let's just do that. Set them all equal to x. And so here we're going to have 4 to the exponent of x. Let's move this more here. So 4 to the exponent of x is going to equal 8 root 2. And so we want to get a common base. The common base is 2 here. So 2 to the exponent of 2x is going to equal 2 to the exponent of 3 multiplied by 2 to the exponent of 1 over 2. And so that's going to be 2 to the exponent of 2x is equal to, so 3 plus a half is going to be 7 over 2. Drop the bases, we have 2x is equal to 7 over 2. Divide by 2, we get x is equal to 7 over 4. Okay, so yeah, so actually let me shift this over so there's actually more space. Yeah, so that's that one. Now for the next one here, so 5 to the exponent of x is equal to 1 over 5 root 5. Common base is 5 here. So we can change this to 5 to the exponent of negative 1 multiplied by 5 to the exponent of negative 1 half. And then we have 5 to the exponent of x is equal to 5 to the, so we add these together, we get negative 3 over 2. We can drop the 5s to get x is equal to negative 3 over 2. Okay, and then this next one here, so root 2 to the exponent of x is equal to 32. Common base is 2 here. This can be written as 2 to the exponent of 1 over 2x is equal to 2 to the exponent of 5. Can drop the bases. 1 over 2x is equal to 5. And then multiply both sides by 2. X is equal to 10. All right, this last one here, 1 over 8 to the exponent of x is equal to 16. Common base here would be 2. We can change this to 2 to the exponent of negative 3 and multiply it by x. That's already in the exponent, is equal to 2 to the exponent of 4. Drop the bases. Negative 3x is equal to 4. Divide both sides by negative 3. X is equal to negative 4 over 3 is what we would get. All right, so what you can do for homework is there's these practice questions here that involve converting from exponential form to logarithmic form or from logarithmic form to exponential form. There is also a Desmos activity on logarithms as well that I would recommend that you complete as well. All right, well, thank you for watching this video lesson, and I hope you have yourself a great day.